Hello everyone. In the last lecture, we studied one method of finding particular integral known as general method. In today's lecture, we are going to solve few examples through which we will try to understand the general method of finding particular integral of the given differential equation. So let us consider few examples. Consider the first example. Solve the differential equation d square plus 3d plus 2 of y is equal to sine of e raised to x, which is the given differential equation of order 2, and the right hand side function f of x is sine of e raised to x. Now we want to obtain the general solution to this non-homogeneous differential equation. We know that non-homogeneous linear differential equation, its solution is given by y is equal to complementary function plus particular integral. So let us see the solution. First of all, we will try to obtain the complementary function, for which we require auxiliary equation, which is given by d square plus 3d plus 2 equal to 0, whose roots are -1, -2, which are real and distinct. Therefore, recall the case 1 of finding complementary function, using which we will be getting complementary function CF, or it is also denoted by YC, is equal to C1 e raised to minus of x plus C2 e raised to minus 2 of x, minus 2 into x minus x. We call this as 1. So which is our required complementary function. Now we will go to find particular integral to the given differential equation. To find particular integral, it is also denoted as yp. So yp is equal to 1 upon phi of d of f of x. This phi of d is the polynomial in D. In this case, it is d square plus 3d plus 2, and f of x is the right hand side function, which is sine of e raised to x. We factorize this polynomial into linear factors, which are 1 upon d plus 2 into d plus 1. Now first we are going to operate this 1 upon d plus 1 operator on the function sine of e raised to x using general method, which is 1 upon d plus a of f of x is equal to, so this will be operated as e raised to minus ax integration e raised to ax f of x dx. In this case, our a is 1. So replace a by 1. That will gives us yp is equal to 1 upon d plus 2 as it is e raised to minus x integration e raised to x into sine of e raised to x dx. Now we want to solve this integration. This is very simple. Either we can make the substitution for e raised to x as t, and then we will use by part rule, or else use the ready formula, which is integration e raised to x sine of e raised to x dx is equal to minus cos of e raised to x, which gives integration as minus cos of e raised to x. Now we are going to operate this operator 1 upon d plus 2 on this function, again using general method. So whatever formula we used in the previous slide, in that please replace a by 2. That will give us yp is equal to minus e raised to minus 2x integration e raised to 2x and this function as it is dx. Simplify this term. that will gives us yp equal to minus e raised to minus 2x integration e raised to x into cos of e raised to x dx. To simplify this integration, now we will use the formula integration e raised to x into cos of e raised to x dx is equal to sine of e raised to x, and that will gives us yp is equal to minus e raised to minus 2x sine of e raised to x. So which is the required particular integral which we have obtained using general method. And therefore, general solution of the given differential equation is y is equal to complementary function plus particular integral, that is yc plus yp. Replace the expressions of yc and yp here, that will gives us y is equal to c1 e raised to minus x plus c2 e raised to minus 2x minus e raised to minus 2x into sine of e raised to x, which is the required general solution. Let's move on to the next example. I hope you have got this example. Example, solve the differential equation d2y upon dx square plus dy upon dx is equal to 1 upon 1 plus e raised to x. Solution. Now get the auxiliary equation, which is d square plus d is equal to 0. Roots are very simple, 0 and minus 1. Therefore, the complementary function yc is equal to c1 plus c2 e raised to minus x. Now we will obtain particular integral. So yp is equal to 1 upon phi of d of f of x. Here phi of d is d square plus d and f of x is 1 upon 1 plus e raised to x. Now we factorize phi of d into linear factors, which are very simple, 1 upon d into d plus 1. Now we will operate this 1 upon d plus 1 operator first on the function f of x using general method, which gives us, using this formula, which gives us yp is equal to 1 upon d into, so replace this a by 1, which will gives us e raised to minus x into e raised to integration e raised to x f of x, which is 1 upon 1 plus e raised to x dx. So this integration is very simple. It is of the type integration f dash of x upon f of x into dx, and we know that what is its integration. So use that formula, we will get yp is equal to 1 upon d e raised to minus x, and this one is the integration of integration f dash of x upon f of x dx, which is log of f of x. So here it is ln log 1 plus e raised to x. Now we have seen that 1 upon d, it is nothing but the antiderivative operator, which is the integration. So evaluate the integration of this term. Use the by part rule here, that will gives us minus ln 1 plus e raised to x into e raised to minus x minus integration minus of e raised to minus x into e raised to x upon 1 plus e raised to x dx, which we have obtained using by part rule. Now simplify this second integration. So take the e raised to x common, that e raised to x will get cancelled, and we left with first term as it is minus e raised to minus x divided by e raised to minus x plus 1. See, purposefully we have taken e raised to x common, because of which our denominator it become now e raised to minus x plus 1. If you observe, derivative of denominator is in numerator now. So which is of the type f dash of x upon f of x, integration of f dash of x upon f of x. And we know what is its formula. So therefore integration is particular integral is equal to first term as it is minus its integration is ln of denominator, which is e raised to minus x plus 1. Now we are going to simplify this term further. Here we are going to express it as 1 upon e raised to x, and we are going to simplify this term. That will give us, simplifying last term, we will be getting yp as yp is equal to minus ln 1 plus e raised to x into e raised to minus x minus ln 1 plus e raised to x minus ln e raised to x. Now take this minus sign inside the bracket. That will give us yp as like this. So at the end there will be plus sign. Simplifying again this last term, it will give us x at the end, which is the required particular integral which we have obtained using general method. And therefore the general solution of the given differential equation is given, which is given by y is equal to complementary function plus particular integral, that is yc plus yp. Now replace these terms by their expressions. Therefore y is equal to c1 plus c2 into e raised to minus x plus x minus ln 1 plus e raised to x minus ln 1 plus e raised to x into e raised to minus x, which is the required general solution. I hope you understood this. Thanks for watching this video.